Welcome. Today, let's have a look at day 8 resonant collinearity for Advent of Code 2024. For this problem, we're given a grid with these characters, and these characters represent an antenna on a specific frequency. If the antenna is of the same character of another antenna, that means those antennas are within the same frequency. If two antennas are required to create what are called antinodes. The way we create antinodes go as follows. Two antennas create two antinodes, and the antinodes would be placed at, in essence, what would be the Manhattan distance of the original antenna. So for example, these two A antenna are in Manhattan distance are what, one to the right, two down. So from this bottom right A, if we go another one to the right, two down, this would be the location of the antinode. And moving up to this top A here, we would move one to the left and two up, and that would be the other location of the antinode. And here we have three antenna, and notice how they're all on the same frequency, meaning they're all the same character. And sorry about that. And again, so the Manhattan distance between these two, this one and this one, diagonal, are the same as before. So it would be what, two up, one to the left. This one would be, well, one right, two down, one to the right, two down. However, now we need to calculate this antenna and this antenna. So this one is, if we consider this A, so this would be what, 1, 2, 3, 4 to the right, one down. So that would mean we go 4 to the left, one up. So that's the location of this antinode. The other antinode would be off the grid, so we don't count it. Now considering this antenna and this antenna, they're, what is it? What, one down, 3 to the left, one down, 3 to the left. So notice how that is why this antinode exists. What they're asking us to do is considering this grid, well, not this grid, but maybe this grid, the original one. They would like us to, if we position the antinodes due to the placement of the antennas, how many unique antinode positions would there be? And it so happens that there are 14. There are 14. So let's go over how we do it. Okay, so the data looks something like this. Well, so here's the test data. So again, I just stripped a new line character and I looped through it. So I just stripped the new line character and I convert the string into a list so that each cell has a character. I probably could have merged this and that together, but I decided not to. And then I use a default dict because what I want to do is I want to store the locations of the antenna. And the key of the default dict will be the letter, or in this case, the frequency. It would be, they tell us that the frequency can be indicated by a lowercase letter, uppercase letter, or a digit. So so I create the default dict. I set the values of the row and column using the grid, and then I loop through each cell of the grid, and I just, well, for convenience, I set the frequency equal to that character or that antenna, and then I ask myself, is that frequency equal to a dot? If it's not equal to a dot, it has to be an antenna, and I add that location to that frequency's listing of locations. So that's that. And then, so we can print it out here just for clarity's sake. For kv in d.items, print kv, I'll just print this here. And then we'll use test data. And then we can do this here. Python problem 8. Well, prob 8. So there are 4 locations for this the 0 antennas, and 3 locations for the A antennas. So that coincides with what we have here. So I simply have stored the locations of these antenna. Very good. Now let's continue. So what I do next is I loop through all the locations for every character. So this first one would be the zeros, and so this locations would be all of the 0 locations. So what I do is I want to generate the antinodes for each pairing. So I want to generate the antinodes between 1825, 1837, 1844, and then move on 25, compare 25 to 37, 25 and 44, and so on and so forth. So that's what I do here in this double for loop, and I pass in the location for each of those, and then I return the count, because I return the count. Either it could be 0, 1, or 2, and I store the count here, and then I just print it out. So let's see what this function find count does. So find count accepts both points, and what I do is I store the delta row, delta column. So this part was a little bit messy, but it works, and it's not too messy. So what I do is I say, okay, which one is the low row, which one is the low column? So then I compare, I say, okay, if R1 is the low row, so imagine if it's the low row, so it would look something like this. That means this would be here, and suppose the other one would be, suppose here. So if R1 is the low one, which is up here at the top, that means that we need to continue up here somewhere to the left. That would be where the antinode goes. So we would continue in that direction. So here is where I store the delta row. And so my point is, if this R1 is this guy, the antinode most closest to, or closest to this antenna would be an up. So that's why I subtract dr. And that means, so if R1 is the low row, then R2 has to be the high row, which means that I have to add. So that would mean that the new antinode goes there. That's why I add this here. Hope that makes sense. I wonder if I can do this here. Maybe you go here. Okay. And then same thing for the columns. Then I say, okay, if C1 is the low column, so that would be here, then that means we would subtract DC, which is what we've done here. We would subtract it. I just showed it earlier. I showed earlier just unintentionally, I showed the row and the column being moved, but I apologize. And if C1 is the low, so C1 was the first point, yeah, and that means BC is the high one, or most to the right, so that means we add more to that one, so that means this guy goes here. And basically just the inverse here, just the inverse of that. So if R1 isn't the low row, that means R1 has to be the high row, which means it's the one up here. So then we'd have to add dr to it, which means it's going to go more down. If you'd like a more thorough explanation on that, just leave a comment and I'll do it. If somebody has a cuter way, and let me know. I'm all ears. I'm more than happy to hear about other people's approaches. Yeah, I'd like, this isn't the prettiest thing, but it works. And moving on, I check if this new row and new column are in bounds and it's not in the set. If it's not in the set, I add it to the set and then I add a count to it. And then I play for, I think just for I think for debugging purposes, I added the hash count, the hashtag, but I don't think I needed to. And same thing here. So if the BR, so that was if this new, oh, I already deleted it. Sorry. If the new anti-node is in bounds and it's not in the set, then I add it to the set, and then I increment the count. I return the count, and so that's how we get here. And we can run it, and I think, well, I already run it, so we get 14, which is what was expected. Yes, 14. So that wasn't too bad. I think it took me a while to, I think, figure out. I think the hardest part for me was for this one was to figure out this portion here. I just had to go slower than I wanted to. And I was trying to avoid this, but I just had to do it. I couldn't think of anything cuter. Maybe it'll come to me later. For part two says there's, I think I initially said before I started Advent of Code 2024 is that I have difficulty, because the prompts are so long, I have difficulty sometimes understanding what they mean. Besides them being long, just sometimes I don't understand them. This was that example or that instance. So what I didn't realize was they say, I just didn't understand that. Now they say that, remember for part two that you can create two antinodes? Now they're saying that you can create as an infinite amount of antinodes as long as you're on the same line and in the bounds. So prior, this would have been the only antinode created by this T and this T. However, now if we extend it on and on, this would be a valid antinode, this would be an anti-valid node. So that's one thing that's new that I couldn't quite understand. I didn't understand that at all. Now I do, of course. In addition, they add another curveball where now these antenna, what were previously antenna, they're also antinode now, because for them they lie in the same line. So anything in this line following the Manhattan distance separation is an antinode. So notice how they say, in this example, there are 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that was new. And it took me quite a while just to understand that. Maybe too long. Much too long. Once I understood that, then the problem is easy. Or not easy, but less difficult. Again, the hard part for me for this problem, believe it or not, was just to understand what they're asking of me and what is the context. So let's move on how I solved it. So for this one, so if you can imagine, I need to somehow create a loop that calculates this first antinode, this second one, and this third one. So that would mean I have to ditch this approach, which was fine by me. So I was more than willing to create a new file. So for the new file, a lot of it is the same. So this is still exactly the same. This is different. What I decided to do was ditch the count and use the length of the set. So we store, remember they want I think it says somewhere they want the unique, what does it say? Yes, how many unique locations. Because it is possible that some antinodes lie on the same location, so they want the unique locations. So I decided to just count the set. And so here we go. So notice how I modified this function compared to the last one. So this is a little bit dirtier. So whenever the complexity rises, sometimes some refactoring is required. So as indicated by the prompt is that now that means that some of the new antinodes will occur at the position of each antenna. So now these antenna become antinodes. So what I do here is I add them. So as soon as we go into this count, now I add them. Those antenna, these were used to be antenna, now they're antinodes. And what I do is I do a little bit of a perspective trick here. So I say, okay, suppose I consider the base node R1 and C1. That's the base one. So I want to calculate the delta row, delta column. So when I consider the base node R1 and C1, I subtract in this manner. And that's how I get my delta row, delta column. And so let me just give you an example real quick. So suppose we have 2, 2 and 5, 3. So notice in this case, this would be the upper left and this would be the lower right. So if we're moving towards, now imagine we're moving off to the toward left direction. So in this case, dr and dc would be, according to this approach, would be 2 minus 5, which would be -3, and 2 minus 3, which would be -1. So this would, continuing off, if you keep adding these values to this would take you off to the upper left continuously. So that's what I did. And notice how I just simply reversed it here. So this was, again, I considered R1 and C1 as my base. Over here I considered R2 and C2 as my base. And this would take you off in the other direction. That would give you +3 and +1. So, and then I just check the bounds. So I set R and C equal to that first, this first node, or yeah, sure, first antinode. And then I check if adding dr and dc to it, if that's still in the bounds, and then if so, I add it to the set, and then I update R and C to that, and then I just keep doing it as much as I can. As long as some R and C are within bounds, then it'll be added to the set of antinodes. Then I do the same thing here. It's just almost exactly the same, except the only thing different is this part here and the setup. So now I consider R2 and C2 my base nodes to get the delta row, delta column. Now I set R and C equal to the second node, and then I just traverse on as far as I can. And that's it. I just count the number of elements in the set, and well, let's run it and let's see what we get. So we should get, what do we get? We're supposed to get what, 34. Okay, so let's do that. So sorry, we're using I haven't changed the test data. Okay, there we go. So we get 34. So there it is. It wasn't too bad, but we'll take it. We'll take it. Okay, if you felt this was good and educational, or it was beneficial in any way, consider liking it or subscribing. Other than that, have a wonderful day or night, and take care.